Hello everyone, I am Abhishek Ranna and this is my solid state physics term paper presentation on SQUID. Yes, SQUID, you heard me right, but not this SQUID. After all, this is a physics presentation. SQUID stands for Superconducting Quantum Interference Device. Cool acronym, right? This is probably the most widely used quantum device in the world today and is so much more cooler than its name. There are three key quantum mechanical effects crucial to the operation of SQUID. The first one is very popular and you must have heard of it, superconductivity. The next is relatively less known, the Josephson effect. We will discuss more on Josephson effect later on in this presentation. And the last is magnetic flux quantization. Similar to the quantization of angular momentum of electrons orbiting atoms, in a superconducting ring, the flux passing through it must correlate to a quantized phase matching like in the green ring. Only quantized values of flux are allowed to pass through. These three effects are essential to understand the SQUID. Superconductivity was discovered in 1911 by Dutch physicist K. H. Owens. While trying to measure the residual resistivity of mercury at liquid helium temperatures, he found that below a certain temperature, the resistance becomes zero. Not only in mercury, he found similar effects in many other materials and called them superconductors. This allowed charges to move with perfect efficiency without energy loss with zero resistance in the lattice. Another interesting discovery regarding superconductors is the Meissner effect, where below the critical temperature, the superconductor does not allow any magnetic field to penetrate, hence behaving as a perfect diamagnet. The first microscopic quantum theory of superconductivity was given by Bardeen, Cooper and Scheffer in 1957. So how does BCS theory describe superconductivity? It involves two electrons bound in a Cooper pair coupled over the order of several hundred nanometers interacting in the lattice that is spaced on the order of just a few nanometers. When an electron moves through the lattice, it disrupts the positive ions near to it, creating a ripple. And when the next electron moves into this region, it is attracted to these displaced positive ions. The attraction between these two electrons creates a binding energy. The temperature must be low enough not to disrupt this binding. The effect can be arrested in a Feynman diagram where the phonon symbolizes the lattice vibration. In this video, we see how the disturbance in the lattice due to one electron attracts another electron towards it, forming a pair. In 1962, Brian Josephson theorized the effect that can happen between two superconductors connected via a weak link like a dielectric or a metal. This is the representation of such a Josephson junction, showing two superconductors separated by an insulating layer. This diagram represents the Cooper pairs tunneling through the insulating layer into the other superconductor without any voltage running through the device. This is similar to quantum mechanical tunneling of electrons through a potential barrier. The current due to this tunneling is proportional to the phase difference of the Cooper pairs on either side of the junction. This no voltage current relation is called the DC Josephson relation. In case of a biasing voltage, the current picks up a time dependence like this and oscillates, hence called the AC Josephson relation. There is a critical current that this device is able to hold, and it depends on the geometry of the junction, choice of the material and operating temperature of device. In 1964, the DC SQUID was invented at Ford Research Labs. To construct a DC SQUID, we take two superconducting half rings and connect them via insulating layers, creating two Josephson junctions in parallel. The critical currents of both the junctions are equal. Now we attach leads on both the sides and pass current through one lead. By Kirchhoff's law, the total current entering and exiting the system must be the same. This applied current goes halfway on one side and half on the other side. So effectively making the maximum allowed current in the device that can show Josephson effect equal to twice the critical current of the junction. By applying a magnetic flux through the device, we establish a phase difference between opposite sides of the ring. A circulating current appears due to this applied flux and supports the applied current in one arm and opposes the current in the other arm. This is where the quantization of magnetic flux comes into play. The circulating current will increase proportionally with the applied flux until a point corresponding to half the quanta. Since the circulating current is proportional to the energy, at this point it is energetically favorable to reverse the direction but maintain the same magnitude, and once again restoring to the original state at exactly one integer value of the quanta. Since there is a phase mismatch between the two Josephson junctions, a positive circulating current will cause the lower side of the ring to reach the critical current first before the opposite side. This oscillatory behavior is calculated to be of a form in a cosine function of the applied flux. We see that this oscillation is shown in a graph where, as expected, at 0 and other integral values of flux the current is maximum, while at half integral values it is minimum. This behavior is periodic and persists with higher values of applied flux. This shows a practical DC SQUID where the voltage measurement is taken across the lead. With this voltage measurement, we can plot a current versus voltage graph. We see for zero flux, we get a characteristic IV curve corresponding to the maximum current at zero voltage. But when we apply a magnetic flux, we get the other curve corresponding to minimum current for one half of flux quantum. If we apply a bias current through the device so that we are sticking strictly to this line, we see that the voltage moves back and forth between the minimum at integer values and maximum at half integer values. Exactly as predicted, the voltage inside this device has a period of one flux quantum with maxima at half integer values and minima at integer values. This behavior closely resembles interference experiments in wave optics and hence is the final piece in the SQUID acronym, the interference. Generally, quantum effects are difficult to see in real life scales, but in SQUIDs we have already achieved that. So sometimes we refer to this as macroscopic quantum interference. The SQUID was designed to measure extremely small changes in flux. As we see in the previous graph, the change in flux corresponded to a change in voltage. The direct measurement of small flux values were extremely difficult in past and hence limited the resolution of our experiments. But the small voltage measurements through SQUIDs can be made by any conventional electronics. SQUIDs are the most sensitive kind of detector that can detect magnetic fields of the order of 10 to the power minus 12 Tesla. This is the energy equivalent of moving an electron 1 millimeter in Earth's magnetic field. Being a quantum device, SQUID is only limited by quantum uncertainty principles. A variety of instruments can be made using SQUIDs as sensors, such as the magnetometer, which through a series of pickup coils and flux transformers is used to measure magnetization of thin films and bulk materials. SQUID-based voltmeters are extremely sensitive and can measure voltages of the order 10 to the power minus 14 volt, and gradiometers which can also measure small changes in the gradients of the field. That concludes my presentation. I hope you enjoyed listening to me. If you want to learn more, you can check out my term paper in the link given below.